so in the last video I said that the two main things that we're going to do in this class with this term, this integral dq over dq over t, is it's either going to be adiabatic, so we're going to assume it's 0, or we're going to use it as a tool. Well, I'll put it this way. We could have heat transfer occurring at a constant temperature. And we'll talk about that here in probably the next few videos. Now, but if it is adiabatic, okay, and what are we, Steve, what the heck are we doing? We're talking about isentropic processes. Well, here's what you need to know. If, and only if, I double F, if you have adiabatic, excuse me, and it's reversible, if you have those two things, adiabatic and reversible, I'm going to draw an arrow here. This is not an equal sign. I'm going to draw an arrow and say that it's isentropic. Okay? Excuse me. Now, why the arrow? Again, remember the second law. The second law says that if I add up all of the heat transfer divided by temperature and add to it the entropy generated, this gives me the entropy change. So if this is 0 and this is 0, then this change is 0. Right? That's the whole point of what we're talking about here. If this is 0 and this is 0, then the change is 0. Now I will tell you this, there are instances where the change is 0 and we're generating entropy. Right? So this could be 0 and this is not 0. And how does that work? If this is 0, this is not 0, what do we know about this? Because this has to be positive, remember? If we lose heat, right, so if this is negative and it's equal and opposite of this, then this could sum up to be 0 and it could still be isentropic. It's kind of a, I would say it's a special case, but it's really not. I mean, we can see this with a lot of steady flow devices. So it's not at all impossible to have this and this both be non-zero and have an entropy change of 0. Okay, just be aware of that. This is an arrow. If I know it's isentropic, I don't necessarily know that it's adiabatic and reversible. But if I know it's adiabatic and reversible, if I know this is 0 and this is 0, then I know this is delta is 0. But if I know this delta is 0, this could be positive and this could be equal and opposite negative, and they cancel out, if you will, or add up to be 0. Okay? So just be aware of that. This is an arrow. If I know it's isentropic, I don't know adiabatic and reversible. But if I know adiabatic and reversible, I do know it's isentropic. Okay? I hope that makes sense. I've kind of repeated that 2 or 3 times because that is a pretty complex subject there, but it is important. Just to kind of be aware of that. Okay. So, where do we go from here? Well, I've got an example now. Let's look at this example problem. I've got an example here. I've got L18. This is page 3. Keep me organized. What do we got? We've got an example problem here. So, I'll try to write a little more clearly. I apologize. Given example problem. What do we know? We've got R134A. That is our substance. We've got saturated R134A vapor enters an adiabatic compressor. Wow, they've told us a lot right there in that first sentence. I've got R134A. I've got a compressor. It is adiabatic. Okay, they've told me it's adiabatic. And they've told me that I've got saturated R134A vapor. So I'm just going to write that as X1 is equal to 1. You could write out the word saturated vapor. You're only going to use the quality whenever you're dealing with a saturated substance, and 1 means 100% in the vapor phase. So this is 4 characters. If you wrote saturated vapor, that's considerably more characters. I don't know how many you can count if you like. The minimum power input to the compressor is to be determined. Also determine the exit temperature. They've given me some other properties here. They told me the inlet pressure is 160 kilopascals, and the exit pressure is 900 kilopascals. And they've told me the volumetric flow rate at the inlet. So they're saying saturated R134A vapor enters steadily at a rate of 2 cubic meters every minute, 2 cubic meters per minute. I'll probably convert that to per second here in the near future. They've told me one more thing there. Pause it, look at it, and see if you can figure out. They've told me at least one more thing that I need to write down here. So go ahead and pause it if you don't know yet. Alright, you got it? What did they tell me here? They told me something very important. Right? Now, it's brand new. The minimum input. What does that mean? They've told me, again, they've told me that this is the best possible version of a compressor. Again, the purpose of a compressor is to put power input into the fluid stream, to increase the energy of the fluid stream using a power input. The compressor, the best compressor, is going to use the least amount of work to do that. Now be very careful, don't get stuck on the word minimum, and don't get stuck on the word maximum. I could change this to be maximum and say determine the maximum power input to the compressor. Well, the maximum power input would be one that's about to blow up, where we're dumping a whole bunch of energy into it and it doesn't have anywhere to go. Maximum doesn't work here, so don't get stuck on the words maximum and input, maximum and minimum. Think about the purpose of the device. In this case, a compressor consumes input. We don't want to put any more input into it than we have to, so the best possible compressor puts in the minimum input. Okay? Think about the purpose of the device, and what are they telling you about it? They're telling me this is the best possible version of a compressor. It's the one that consumes the least amount of work to do this job. They want us to find a power input. Again, that's a work rate. Power is work rate. And they want to find the exit temperature. They want us to find T2. So this is what they're asking for. Okay. So what are some good tools we could use to find a power input? We just got done with exam 2, which is all about the first law, so I'm hoping your gag reflexes at this point is, Steve, that's an energy term, use the first law. The first law is all about energy. So if we set up a first law for this compressor, how do we do that? Well, simple thing to do is draw your compressor, draw your system, and I draw the reverse of a turbine. So what's crossing the boundary? Well, a compressor always has mass crossing the boundary. I go from I say the compressor squeezes it down, okay, and it does that by putting what? A power input. So the basic compressor has these three energy quantities. We should know that from chapter 5, okay. Power in, mass, mass. What else could cross the boundary? Well, it could be heat. Do we have heat here? No. Adiabatic. Told us no heat transfer. So looks like the first law, again, just add the in, subtract the out. So I've got power input is equal to the difference, or power input plus the energy of the mass in minus the energy of the mass out is equal to 0. Okay, well, we know there's going to be an enthalpy change. It's always a safe assumption there's going to be an enthalpy change for the mass. Is there a kinetic energy change? No, they didn't give me speeds. It's not a nozzle or diffuser. I can't find the speeds. If I had the areas, I could probably find the speeds, but I don't have the speeds. They're not asking for the speeds. I don't have the areas. I can't find them. So we're just going to assume that, we're going to assume a couple of things here. I don't think they told me that it's steady flow. We are going to assume that it's steady flow, so I don't have a differential equation on my hands. Again, this is dE dt over here. If I assume steady flow, the right-hand side, the change goes to 0. And they did not tell me enough information to worry about the kinetic change, so I'm just going to say that the kinetic energy at the inlet is equal to the kinetic energy at the outlet, or at least the change is negligible. Okay, so what do we know here? Can we find, we're looking for the power input, that's what we want. Can I find the m dot? Well, I don't have the m dot right off, but I do know the volumetric flow rate. And remember, if if I use the volumetric flow rate and the specific volume, I can use that to find m dot. Okay, so that's, I think we can find m dot. That does require us to be able to find V1. Next things, can I find H's? Well, I know it's saturated vapor and I know the pressure. Yes, I should be able to find H1 and little V1. All right, so let's write that out. Let's see if we can solve the first law right off. Properties. Given P1 and X1, I can use that to solve for find in the property tables, because it's R134, so we're going to use property tables, H1 and V1 found off these two properties. Okay? What about H2? Well, what do I know about state 2? I know the pressure at state 2. Right? So I need two properties to find H2. I know the pressure at state 2. What else do I know? Now, a common mistake I see is people will say, Steve, it's saturated vapor, right? No, we don't know that. Saturated vapor enters. We don't know that saturated vapor exits. That's not given to us. In fact, it's not going to be in a compressor, saturated vapor at the exit. It's going to be superheated, most likely. Okay? I know you don't have any reference to know that, but I can just tell you from experience. They didn't tell us it exits as a saturated vapor. This thing would have to lose a lot of heat for it to do that, and this one's not losing any heat. So when it exits the compressor, it's probably going to be a superheated vapor. So I need a second property here. I don't have a second property, right? Not immediately given. So what other property could I use? Well, what else do we know? Pause here if you want to take a stab at it and see how we do. Right? That's always a good way to talk to you guys about solving problems, practicing. Go look and see if you can figure this out, and then go back and look at the solution. So I'm going to give you the solution here in a second. So if you want to pause it and see what other property can I use at state 2 to try to figure this out, go for it. Okay, so you either come back victorious or defeated, and that's okay. As long as we learn and get better, that's no problem. Okay, so what are we going to use to find H2? I know pressure. What's my second property? Well, what else do we know? Do we know any other laws or equations that might help us get to state 2? Well, what's the whole purpose of this chapter? Second law, right? The purpose of this chapter is the second law. I'll set this over to the side. I think we're okay for the moment. The purpose of this whole chapter is the second law. So let's draw the second law for this thing. What is the second law? Is this a process from state 1 to state 2? Sure. I've got an inlet we're calling 1 and an exit we're calling 2. I think we can use that. Which one do we use? Well, we could use any of them, I think. It is a control volume, so if you wanted to use this one and say, well, m dot times little s2 minus little s1 is equal to the integral of del q dot over t plus big S gen dot, that's okay. You could use any of the three forms of the second law that we drew out last time, right? You could use any of these three. I picked this one because it's a control volume, but I could use this one because I don't know the mass flow rate yet. This one's probably better for a closed system, but it would still be applicable in this situation. They're all useful. Just which one should I use? I don't know. Let's try this one and see how it goes. What do I know about the heat transfer? 0. What do I know about the entropy generated? 0. Remember I told you guys, if it's adiabatic and reversible, then you know it's isentropic. I need to know these two things. If I know these two things, then I know it's isentropic. I know these two things. Little s2 minus little s1 is equal to 0, or little s2 is equal to little s1. Can I find either of those? Well, sure. I can find these. I can find s1. That'll give me s2. All right, guys, go look these up. I'm gonna write these down so you don't have to watch me look them up. But go look them up, and I'll have them at the beginning of the next video. But this is good practice. You should be able to do this quickly. Find these properties. Okay. One of them you're gonna have to interpolate probably, and that's okay. So give me properties, and we'll be back.